Page 11 of trig equations and identities. Okay, number 5. If alpha is acute and cosine of 2 alpha equals negative 7/9, find without the calculator cosine alpha and sine alpha. Okay, so now we're going to start working with double angle identities. Let me just write the double angle identities here in the corner for you. Sine 2 alpha equals 2 sine alpha times cosine alpha. Cosine 2 alpha is equal to cosine squared alpha minus sine squared alpha. 2 cosine squared alpha minus 1, and 1 minus 2 sine squared alpha. When do you use each of these three? Well, pay attention to the fact that this one has only sine squared, this one has only cosine squared, and this one has both. You're probably not going to use this one that has both very often, because usually you're going to use this one when you want only cosines, and you're going to use this one when you want only sines. All right? Okay. So let's do this first one. If alpha is acute and blah, blah, blah. So we know that we're going to do something with cosine 2 alpha. Let's see. If we have that the cosine 2 alpha is equal to this, then we could find with this identity, part A, right? Because basically we'll fill this in and then we'll just find out what this is, right? We're not going to use the other two because with the first one it's practically useless because we're still going to have two unknowns, and this one would find part B instead of part A. Okay? All right, so let's put in negative 7/9 on the left side, and then we'll say 2 cosine squared alpha is our unknown, and then minus 1. Now we're just going to do algebra. We're going to add 1 to both sides. So we'll get plus 1 plus 1. So it'll be 2/9 on the left side. And on the right side, it would be just 2 cosine squared alpha. Then we're going to divide both sides by 2. So we'll get 1/9 equals cosine squared alpha. And then we're going to take the square root of both sides. When we take the square root of both sides, remember that one of the sides should be plus or minus because we're introducing the square root. Square root of 1/9 is 1/3. And there's no more squared, right? Okay, so our answer is cosine alpha is equal to either plus or minus 1/3. Okay, now that we know the value of cosine, we don't need to use the double angle identities anymore. We could just use the Pythagorean identity, because if we know cosine alpha, we can figure out sine alpha using the Pythagorean identity. So let's do that. So sine squared alpha plus cosine squared alpha is equal to 1. Cosine squared alpha, or cosine alpha, is plus or minus 1/3. When I square it, I get 1/9 again. So sine squared alpha is equal to 8/9, and sine of alpha is equal to the square root plus or minus of 8/9. So that would be plus or minus square root of 8/3. And this would be our sine value, which is part B. Okay. Oh, they do tell us that alpha is acute. If alpha is acute, that means it's less than 90 degrees, which is it means it's in the first quadrant, right? If it's in the first quadrant, then we know that both the sine and the cosine are positive. So instead of saying that cosine is plus or minus 1/3, we can positively say that it is positive 1/3. And instead of saying that sine alpha is plus or minus 8/3, we can positively say that it's positive 8/3, okay? Because they tell us that alpha is acute. All right, number 6. Find the exact value of this expression. Okay, so first of all, exact value means we're not going to use the calculator. And then you're going to say, but we don't know the sine of the cosine of pi over 12. That's not a special angle. So what we're going to do is we're going to expand this and see if we can do any kind of substitution so that we're using a double angle instead of pi over 12. What's double of pi over 12? Pi over 6. That is a special angle. Kind of sus, right? So let's use the identity a squared plus 2ab plus b squared to expand this a plus b squared, right? So we're going to have cosine squared pi over 12, and then we're going to multiply sine squared by itself. So it'll be sine squared pi over 12. And then in the middle, we're going to have 2 sine pi over 12 times cosine pi over 12. Okay. Ooh, cosine squared plus sine squared, that's the Pythagorean identity. It's equal to 1. So we could replace these two with just 1. And 2 sine cosine, wait a second, that is sine 2 angle. Okay, so it's going to be sine 2 times the angle. And we're kind of done. Let's continue on. 1 plus, and then 2 times pi over 12 would be pi over 6. Sine of pi over 6, that would be 1/2. So 1.5 or 3/2. Okay? All right. 7. Use an appropriate double angle formula to simplify. Okay. 2 sine alpha cosine alpha. Okay, that's obviously this, right? So that's equal to sine 2 alpha. 2 cosine squared beta minus 1. Oh, that looks like this one. So it's equal to cosine 2 beta. 2 sine squared minus 1. That almost looks like this one, except it's inverted, right? So that's just like, you know, instead of putting cosine 2m here, we're going to put negative cosine 2m, right? Because cosine 2m is equal to 1 minus 2 sine squared. But if I put a negative in front of it, then it would be negative 1 plus 2 sine squared. And then I would have exactly that, right? So the negative is the key here. 2 sine 2a cosine 2a. So this pattern here is equal to sine 2 times the angle being 2a, right? And do we need to do anything else? I think that's pretty much it. Then we just say sine of 4a, we simplify. And 1 minus 2 cosine squared 3b, this is almost in the format of this, except it's inverted, right? So we're going to put negative of cosine 2 3 beta. Okay, so that would be negative cosine 6 beta. Cosine squared minus sine squared, that's exactly this identity. So we could just replace this with cosine 2a, which is equal to cosine 4a. All right. 8. Show that this is equal to this. So first thing we do is we ignore this. And we're just going to simplify this. And then when we finally get to the end, we'll compare it back with this to see if we got it. Okay, whenever you have a show that, you need to ignore the right side, use only the left side to try to arrive at the right side. So we have FOIL here, so we're going to do FOIL. And then we see that the middle term is actually the double angle identity, and the first and the third terms are actually equal to 1, the Pythagorean identity. So we're going to put 1 plus the sine of 2 theta. And then we're going to go back and say, okay, what was the left side again? Oh, that was it. We're done. QED. Okay, solve exactly for x, where x is between 0 and 2 pi. So let's see. We're not going to be able to solve this when we have two different kinds of signs here. We have one double angle sign, we have one single angle sign. So what we want to do is we want to replace this with something that has sine x's in it. Remember that there is two sine x cosine x. That's the only option we have here. So I don't really see where this is going, but let's go ahead and put 2 sine x cosine x here. And then we'll factor out the sine x because we have a common factor. I still don't know where this is going. Okay, now we can kind of see where it's going. In order for this product to be 0, either this has to be 0 or this has to be 0. So let's find out. Let's solve each one separately. Let's solve this first. When does sine x equal to 0 between 0 and 2 pi? Well, there's two solutions, right? There's actually there's three solutions. X equals 0, x equals pi, and x equals 2 pi. There's these three solutions. Any of these three solutions, sine x is 0, and this whole thing is equal to 0. Now let's solve the other side. 2 cosine x, not 2x. 2 cosine x plus 1 equals 0. Subtract, what we want to do is we want to isolate the cosine x, right? So we're going to subtract 1 from both sides. We'll get 2 cosine x equals negative 1. Then we isolate cosine x by dividing by 2. Cosine x equals negative 1/2. Cosine x equals negative 1/2. When does that happen? That happens here, and it happens here. So this would be 2/3 pi, and it would happen at 4/3 pi. And I think just those two. So we have 5 solutions. We have these 3 solutions, and we have these 2 solutions. Okay. On this one here, again, the only obvious thing we're supposed to do is we're supposed to replace sine 2x with 2 sine x cosine x. So let's do that first. And then we have 3 sine x equals 0. And then, I guess, let's factor out sine x because it's a common factor. Okay. Again, if this is equal to 0, that would be a solution. If this is equal to 0, that would be a solution. So let's see if these lead anywhere. Sine x equals 0, we just did that. We know that x is equal to 0, pi, or 2 pi. So those are 3 possible solutions. Let's set this equal to 0. 2 cosine x plus 3 equals 0. 2 cosine x equals negative 3. Cosine x equals negative 3/2. Okay, can cosine x ever equal negative 3/2, negative 1.5? No, because remember, cosine ranges from between negative 1 and 1. So no solutions there. So just these solutions here. Okay? And moving on to page 12. Use the double angle formula to show that sine squared equals 1/2 minus 1/2 cosine 2 theta. Okay, so in this case, looks like we're going to use the double angle formula that has sines in it. So let's write that out first. Cosine 2 theta equals 1 minus 2 sine squared theta. I just got this out of the formula booklet or from the last page. Now I'm going to rearrange it so that sine squared is by itself on the left. So first thing I'm going to do is I'm going to subtract 1 from both sides. So I get cosine 2 theta minus 1 equals negative 2 sine squared theta. Then I need to further isolate sine squared theta by dividing by negative 2. So I divide by negative 2 both sides. And I end up with negative cosine 2 theta divided by 2 and positive 1/2 equals sine squared theta. Did I get what I needed? 1/2 minus 1/2 cosine 2 theta minus 1. It worked. QED. Notice that in this case, they didn't explicitly say what we were supposed to start out with. They just said here, use the double angle formula. So then I started with this, right? And then I got this relationship at the end. All right. 11E, trig equations in quadratic form. Okay. So these will be a blast from the past. You've done this in the past with exponentials. So let's do it with sines and cosines. Okay, so the domain, remember, is between 0 and 2 pi. So we have 2 sine squared x plus sine x equals 0. This is actually a quadratic. It's kind of hard to see unless we replace our sine x's with t's. If we replace our sine x's with t's, we'll have 2t squared plus t equals 0, right? And then if we want to solve this equation, it's good to factor out the greatest common factor, 2t plus 1 equals 0. Now that it's factored out, we can replace the t back with sine x and go back to the original form. Sine x times 2 sine x plus 1 equals 0. We know that either this is equal to 0 or this is equal to 0 in order to make this 0. So let's solve those. Sine x equals 0 is one of the equations, and the other equation is 2 sine x plus 1 equals 0 with this domain. Sine x equals 0 with that domain, it would be either 0, pi, or 2 pi, right? Those are the values that make sine of x 0. Now let's do this one. We need to isolate sine of x. So first we're going to subtract 1 from both sides. 2 sine x equals negative 1. Then we're going to further isolate sine x by dividing 2 both sides. So we'll have sine x equals negative 1/2. What triangles have a sine of negative 1/2? It would be this triangle here and this triangle here. These are 7, 6 pi and 11, 6 pi. Those are the two angles that give a sine of negative 1/2. So these are 2 of the solutions, and these are the other 3 solutions. All 5 are solutions. Okay, next one. 2 cosine squared x plus cosine x minus 1 equals 0. So again, in order to see that this is a quadratic, I'm going to replace my cosine x's with t. 2t squared plus t minus 1 equals 0. If I factor this, it's going to factor into, and you can use quadratic formula to factor this. It's going to be something like this. It's either going to be plus minus, or it's going to be minus plus, because there's a negative here. So when we multiply it together, it has to be negative. Let's see which one works. So if this is plus and this is minus, then the middle term would be negative 2t plus 1t, and so that would be wrong. So not this. So that leaves this, 2t minus 1 and t plus 1. So if I multiply 1 times t, that would be negative 1 times t, that would be a negative t, and then 1 times 2t would be a positive 2t, and that would give me a positive t, and so that works. Okay, so my answer is 2t minus 1 times t plus 1. And now what I'm going to do is I'm going to replace back t with cosine x. So I'm going to put 2 cosine x minus 1 times cosine x plus 1. Each one of these factors, if they were 0, would make the whole thing 0. So let's solve that. 2 cosine x minus 1 equals 0, or cosine x plus 1 equals 0. So add 1 to this, and you get 2 cosine x equals positive 1, cosine x equals positive 1/2. What are the values which have a cosine of 1/2? That would be this tall triangle or this tall triangle. So that would be x equals pi over 3, which would be this one here, or this one, which would be 5/3 pi. So those are 2 possible solutions. What about this other one? Cosine x equals negative 1. When does cosine x equals negative 1? That would be this angle here, which is like 180 degrees or pi. So then it would be x equals pi. So those would be the 3 solutions for part C. What about part E? Sine squared x equals 2 minus cosine x. The problem with this one is it's got sine and cosine. We want only sine or only cosine. Now remember, it's pretty easy to shift between sine and cosine if you have a sine squared or a cosine squared because of Pythagorean identity. We know that sine squared plus cosine squared equals 1. So sine squared is equal to 1 minus cosine squared. So we can replace this sine squared with 1 minus cosine squared instead, and then we have just cosines, and that's nice. Okay, so now let's put everything on the left side and leave 0 on the right side. So then we're going to have negative cosine squared x plus cosine x, and if we subtract 2 from both sides, that would be minus 1, right? If we did minus 2 minus 2, that would be minus 1, equals 0. I am going to now replace my cosine x's with t, because then it's a little easier to factor. I don't like this leading negative sign, so I'm going to multiply everything by negative 1. So positive, negative, and positive, and the 0 remains 0. Now I'm going to look at this and see if it's factorable. It doesn't look like it factors with integers. So then I'm stuck with quadratic formula. So negative b, right? Our b value is negative 1, our a value is 1, and our c value is 1. Negative, negative 1, plus or minus b squared, which is 1, minus 4 times a times c, all over 2 times a. So that would be 1 plus or minus the square root of negative 3. So imaginary numbers. So no solutions. Okay, basically, if we replaced t back with sine or cosine of x, we would have cosine of x equal to this complex number here. Never happens. Okay, so no solutions. All right. Number 2a. Again, our domain is 0 to 2 pi. We would like only cosine x's and no cosine 2x's. So let's replace our cosine 2x with the identity that has cosine x's only in it, which is 2 cosine squared x minus 1. So I just replace that with that. Then I'm going to factor this, so I'm going to replace my cosine x's with t. Let me put it in order so that it's easier to factor. Okay, and let's see if this factors. So it would be 2t and 1t and 1 and 1. It would either be plus and minus or minus and plus. Which one works? Looks like it would be this one because this is negative, right? So I think this works. Yeah, so this times this would be negative 2t, and this times this would be positive 1t, and it would work out. Okay, now we're going to put our t replaced back with cosine. So it would be 2 cosine of x plus 1 times t, I'm sorry, not t, cosine x minus 1 equals 0. So we're going to find out when is this 0 or when is this 0, and those would be our solutions. So 2 cosine x plus 1 equals 0. That's the same thing as cosine x equals negative 1/2, right? I subtract the 1 over and then I divide by 2. When is cosine of x equal to negative 1/2? That would be this triangle or this triangle. So that would be x equals 2/3 pi or 4/3 pi. Those would be two solutions. And then the other solution would be cosine of x minus 1 equals 0. Cosine of x equals positive 1. Cosine of x equals positive 1. That would be x equals 0 or 2 pi. So those would be two more solutions. All right. Next one. Again, we're going to replace cosine 2x with something, but this time we would like only sine x's. Cosine 2x is a great identity because you could replace it with things that only have cosine x, and you could replace it with something that only has sine x, right? I just did. I just replaced that with that. Now I'm going to rearrange it so that it's in quadratic order, where I have like descending powers of sine, right? Then I'm going to replace sine x's with t's, because then it's easier to factor. Okay, I'm going to reverse all these negatives, a little bit easier. Okay, and then I'm going to factor. I'll have 2t times, let me do it here, 2t times, or 2t something, 1, and 1t something, 1. And so one of these is going to be negative, and one of them is going to be positive. Let's see which is correct. So in order to get the middle term of negative t, I would need to make this one negative. So then this one positive. So then it would be negative 1 times 2t, that would be negative 2t, and I would have positive 1 times t, and that would give me, yes, so that works. So my answer would be 2 sine x plus 1 times sine x minus 1 equals 0. So the question is, when is this equal to 0, or when is this equal to 0? 2 sine x plus 1 equals 0. That's true when sine of x equals negative 1/2. Otherwise, we're looking for sine of x minus 1 equals 0. That's true when sine of x is equal to positive 1. So sine of x equals negative 1/2, that occurs with this triangle or with this triangle, right? So that would be 7/6 pi or 11/6 pi. And sine of x equals 1, that happens only one time, which is right there, which is 90 degrees, or pi over 2. So there's 3 solutions for that one. Part E, sine of x plus cosine of x equals square root of 2. This is a kind of a weird one, right? There's no double angles here. There's no squareds. So I don't see any obvious way to use the double identity angles here, but they said this was a double identity angle problem. Well, we have sine and cosine on the left side. What if we like squared both sides? If we squared both sides, maybe we'll generate some sine squared cosine squareds. The right side would become a nice neat number. It would become 2, wouldn't it? So let's do that. We're going to do sine plus cosine squared. Remember, we have to do FOIL, so that would be sine squared x plus 2 sine x cosine x plus cosine squared x equals square root of 2 squared, which is just 2. Sine squared plus cosine squared is 1, right? So we could change that to 1. And then 2 sine x cosine x, now that's a double angle formula. Okay, so now we can subtract 1 from both sides, and then we'll end up with 2 sine x cosine x equals 1. And then we could change this into the double angle identity sine 2x. So now we have the same kind of problem that we did last time, a couple pages ago, which was we have a sine with an argument that is a transformed x. So we want to know what angles 2x give us a sine of 1, and that would be 90 degrees or pi over 2. By the way, what is our domain? Our domain is x equals 0 to 2 pi. 0 to 2 pi. And 2x would be 0 to 4 pi. So now that we have our one solution of 2 pi, we can generate other solutions by adding and subtracting 2 pi, or pi over 2. Our one solution is pi over 2. We can generate other solutions by adding and subtracting 2 pi. If we subtract 2 pi, obviously it's going to go below 0, so we're not going to subtract 2 pi. If we add 2 pi, that would be 5 halves pi, because we're going to add 4 halves pi to pi over 2. If we add more than that, it's going to go past 4 pi. So we're just going to add once. 5 halves pi is the one other solution. And then both of these, if we put pi over 2 inside sine, we would get 1. If we put 5 halves pi in sine, we would also get 1. So both of those solutions are correct. We just need to find out what the x domain solution is. We find that by dividing by 2 instead of multiplying by 2. So we would get pi over 4, and we would get 5 fourths pi. So pi over 4 and 5 fourths pi are the two solutions which would make this true in the domain of 0 to 2 pi. Now we're done.